Thank you. Yeah, so first of all, thanks to the organizers for inviting me. It's really always a pleasure to come to Florence, and especially after a long break, so thanks a lot. So today I'm going to talk about some work I've been doing over the past 2 years, more or less, with different people about this subject here, symmetry resolved entanglement, which is essentially a new measure of entanglement that has attracted quite some attention, especially since 2018 in our community. So my talk is not going to be, I think, very technical, because I imagine there haven't been many talks about entanglement in this workshop, probably. So I thought I would do something that is relatively introductory and basic, leaving out a lot of technical details. So if you're really interested, you can always ask me about the details. So the work I have done in this subject oops, that was too fast. It's published, well, it's on arXiv on 3 preprints that you see in there. So we did some work where we looked at different models, really. So Sine-Gordon, Potts model. More recently, we looked at excited states, which is actually what I'm going to talk a bit more in the second part. And there is some work in preparation with the same set of people, which is also about excited states. So I'm going to give you a flavor of all these works very superficially, starting with an introduction to the subject. So as you saw before, when I went too fast, I've done this work with quite a few collaborators, so just let me show you who they are. So I think you probably all know Pasquale Calabrese. He's done actually a huge amount of work in this subject, a lot more than myself. David Horvath is a postdoc at CISA with Pasquale. Luca Capizzi is a student of Pasquale. Cecilia and Michele are my students, and Lucia is a student at the University of Valladolid in Spain, and she came for a 3-month visit recently, and we did this project on excited states. Okay, so structure of the talk essentially is a very, very simple structure. So a little introduction about some reasons why people find this interesting, how can it actually be computed, and what is it? And then in the second part, some of my contributions with a focus on the symmetry resolved entanglement of a certain class of excited states. So here there are just some pictures which are actually a comparison of some formula we got with numerical simulations, and you will understand what this means hopefully a little bit later in the talk. Okay, so introduction. So when we talk about entanglement, there are some very basic definitions we always have to get through. They don't even have anything to do with symmetry resolved entanglement, just simply with entanglement. Actually, I went too fast. That's the next slide. So my introduction actually is about where these symmetry resolved measures come from. So the first papers that I'm aware of where people talk about measures of entanglement that exploit the existence of an internal symmetry in the theory are these papers here. And I must confess, I wasn't really aware of them until just a couple of months ago. So I did write a few papers on the subject without really being aware of this very early work. And the reason is, as often in our community, that later on, other people thought about the same problem in a different context, which was a context I'm more familiar with, the context of integrability, spin chains, and so on. So the first time I came across this idea actually was from the work of Xavier Alcaraz and Sierra of 2018, where they look at the XXZ chain, and they look at the structure of entanglement in that chain. They realized that the U1 symmetry of the XXZ model actually played a role in the structure of entanglement. And then the work that people mostly associate with this subject nowadays is the work of Goldstein and Sela of 2018. Mainly because, well, they propose a very generic method to compute this, which is what we use, but also they were the ones that actually introduced the terminology. So the words symmetry resolved entanglement, they appear for the first time in this work, actually, which was just almost simultaneous with the work of Xavier et al. So one possible way to introduce a little bit what this is actually to look at the abstract of this paper, because in that abstract, there's a good summary of what this is and what are the special features of this quantity. So I have copied here an extract of that abstract. It's actually a lot longer than this. I left out some bits, but there are a few key things already here. So it says the entanglement in a quantum system that possesses an internal symmetry characterized by the magnetization or U1 charge, this is flux Z, is distributed among different symmetry sectors. Okay, so that is the observation. We find, surprisingly, that the entanglement entropy is equally distributed among these different sectors. So this is a property that has been later on, I think, called equipartition of entanglement. So this is a feature that one also finds in quantum field theory in a certain limit. And then they also say its value is given by the standard area law violating log term. So there is a logarithmic scaling of entanglement as for the usual entanglement. If you ever saw the standard formulas, Cardi, Calabrese, and so on, logarithmic scaling, depending on central charge. But then there is a double log correction relating to zero temperature susceptibility. So that we will recover in other models as well. And they say this result provides a new way to estimate simultaneously central charge and critical exponents of some fields. I mean, this last statement here is a bit obscure, but turns out that this log-log term they talk about, it actually includes some constant parameter there, which is the dimension of some field. So the way Xavier Alcaraz and Sierra motivate their study here is that actually this is a new measure of entanglement where one can extract quite a bit of information about the theory, okay, the UV limit at least. Now, there are other people that are inspired to study this for the reasons, and one of the reasons that is often quoted is that actually there is quite some experimental work nowadays where people measure, if not directly symmetry resolve entanglement, then certainly some aspects of it. So, so there's quite a few papers, these are just some of them, and I think actually Pasquale Calabrese is a co-author of at least one of these two. Okay, so this here is a little bit of motivation. Let's now come to the basic definitions I was talking about a minute ago. So if you are studying entanglement, very often you want to look at a bipartition of a quantum system. What I'm going to be studying is always in 1+1D, so this picture is already way too complicated, but it gives you the idea. So you have a subsystem A, and you have the complement A bar, and together they form the whole system. So they're complementary systems. Now, if you have this bipartition, you can define some basic quantities that are always involved in the evaluation of entanglement measures. And the basic quantity usually is this so-called reduced density matrix. So this is a matrix that is obtained by taking the density matrix, the whole density matrix of the system, assuming it is in a pure state, just to make things a little bit easier. So you take density matrix and you trace out the degrees of freedom of the complement of A. And the idea is that when you do that, well, you get something that is a function of subsystem A, but also encodes information about the correlations that exist between these two systems. And so in that way, encodes information about entanglement. Now, once you have these metrics, you can compute different measures, and there is a whole family of them that people have defined and continue to define. So the symmetry resolve entanglement is just one more member of this family, ever-increasing family. But there are some, I would say, most famous measures of entanglement that people study. One of them are the so-called Renyi entropies. So these are dependent on these metrics, as you can see, but they also depend on an index, the Renyi index N. So there is actually a family of Renyi entropies for each choice of this N, which can be integer or not. If you take the limit N to 1 of this quantity, it's easy to show that you get something like this, which is actually the more basic measure of entanglement people study is the von Neumann entropy, or sometimes simply called entanglement entropy. So one way to obtain it is from the Renyi entropies. Okay. So I have done a lot of work in the past 15 years computing, actually, especially these Renyi entropies, because in the context of QFT, especially if N is integer, there is a more clear program to compute those than to compute this, actually. So very often, what we do is to compute this and then do an analytic continuation, if we can, when N goes to 1, to get the von Neumann entropies. Okay, so Okay, so these are some examples, and when we look at the symmetry resolved entanglement entropies, we're going to see that there are some sort of equivalent definitions which are now going to depend on the charge sector of the theory. So you will see similar formulas in a couple of slides again. Okay, so once you have this, you can ask yourself, how do I actually compute these things? And of course, depends what kind of model you're interested in. So people, of course, can do a lot numerically. So numerically, if you have a discrete system, very often by different methods, you can compute this as a matrix. You can compute the eigenvalues of this matrix, and then from the eigenvalues, you can compute any measure you like. So that's the numeric side. But if you want to do something analytically in quantum field theory, then, well, you need some other kinds of methods. So many of you will be familiar with work of Calabrese and Cardi, collaborators, many other people that looked at this in the context of conformal field theory. So if you have conformal symmetry, that gives you some additional information that makes it a lot easier to compute these things. Okay? But if you are away from criticality, like in a massive QFT, you cannot use the same ideas. You need a little bit more. So I'm going to give you, in a nutshell, a very quick summary of one of the leading methods people have been using in QFT to compute these things. So this method essentially, I mean, the summary of it is that it is possible to relate the Renyi entropies in particular to correlation functions of certain fields. And then once you are able to do that, especially in massive QFT, integrable QFT, you can use all the techniques you are familiar with to compute correlation functions. And from those, you can get entanglement measures. Now, how does this connection arise? Well, it is relatively deep as an idea, but the basic elements are summarized here in this slide. So it is known for a long time, and this goes back even before Calabrese and Cardi, already in the work of Larsen and Wilczek, that's 10 years earlier, that well, that this trace of rho to the n that appears inside the Renyi entropy formula is related or can be interpreted as a partition function. It's a partition function that depends on this parameter n. And actually, in this interpretation, it is actually quite important n should be an integer, because now n is going to be the number of sheets in a Riemann surface. So this is the partition function on a Riemann surface with n sheets, where these are cyclically connected along a branch cut, which has a length, which is the length of our subsystem A. So now we are in one dimension, okay? So it looks something like that. This is the example with n equals 3, so three sheets, and you see how they are connected and then cyclically connected. Now, this connectivity, I mean, it can be explained analytically in a better way, but one way I like to understand it is in connection to this trace. So essentially, the fact that there is a trace here is what gives rise to the cyclic connection, and the fact that there is a product of n matrices here is what determines the connectivity of these sheets. So this is directly related to this quantity, okay? Now, at the same time, that Riemann surface turns out to be the space-time manifold, which is associated to the partition function of what we call a replica theory. So what is replica theory? It is whatever theory we started with. Suppose that we wanted to compute entanglement, I don't know, in the Ising model, any model you could think of. So turns out that this trace of rho to the n can be interpreted as a partition function of a model which is made of n copies of that one. For example, n copies of Ising. And these copies are non-interacting, okay? So it's each copy on its own. Okay, and now in such a theory where we have n copies of the original model, we have a huge amount of symmetry, of course. So the whole permutation group actually is a symmetry of that theory. But associated to symmetries, we have fields, okay? Now, the particular symmetry that is of interest to us because of the structure of this Riemann surface is cyclic permutation symmetry. And there is a field, Tn, that is going to be associated with that symmetry in this replica quantum field theory. Now, in our work of 2018, we call that a branch point twist field. Twist fields in general are symmetry fields. And the idea that the trace of rho to the n is related to a correlation function of these fields, actually essentially in this way. So it's the 2-point function of those fields sitting at the ends of this branch cut. This idea already appeared in a slightly different form, but it's already in the famous work of Calabrese and Cardi. So they also realized that in conformal field theory, they could get the famous formulas for entanglement starting from a two-point function. Now, all of what I've told you here is kind of quite old stuff, quite old results, but I'm reminding you of this because it turns out when you do symmetry resolve entanglement, there's also going to be a representation of that in terms of two-point function of some field. It's just not going to be exactly the same field, but a generalization of that. Okay, so from here then, symmetries. So let's say a little bit about what happens if we have an internal symmetry. So we have this replica theory that has lots of permutation symmetry, but inside each of these copies, there could be an internal symmetry. For example, in the Ising model, there is Z2, a discrete symmetry. In a Sine-Gordon model, there is U1. In the Potts model, depending which, there is Zn. So if we have a symmetry, normally we're going to have a symmetry charge associated to that commutes with the density metrics of the theory. And if this charge is local, we can also think that we can sort of decompose it into a part that acts on subsystem A and a part that acts on its complement. And this part that acts on subsystem A will commute with the reduced density metrics on subsystem A, the one I defined earlier. Now, if these things are true, then what will happen is that these matrices, rho A, rho A to the n, are going to have some sort of block diagonal structure. Okay? Now, this picture is not very accurate in the sense that these blocks, they don't all have to be identical or of the same size. They will be possibly different, but you would have some sort of structure like this. So what the symmetry resolve entanglement tries to capture, in a way, is the contributions to the total entanglement of each of these blocks. This is what, more or less, what this is about. Now, how this is formally defined is through well, several quantities are defined in this process. The first one, which Goldstein and Seller introduced in 2018, is this idea of a symmetry-resolved partition function. Yeah? On the boundary, yeah.
Supposing there is a Q that's a bar and also there is a bond later.
Yeah. That's a good question. So, I mean, actually, I'm not sure how strict this requirement is. So, I mean, in principle, there is a quite, I mean, in what I wrote here, there's a strict requirement. Everything is very local. But I suspect that if you are in QFT and you're taking a certain scaling limit, then perhaps it just has to be maybe semi-local, not completely local. But for the sake of definition, for clarity, we'll introduce it like this.
You say the Q is an integral of some density.
Yeah.
Only on the region A.
Yeah.
And not on the region B.
Yeah. So, or it's a sum of two contributions that are separate for each region. Yeah. 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 No, that's a good point. So, I mean, in all somehow, I mean, it appears from the examples people look at, and there are very many, that those terms are either don't have a very, I mean, either are not very relevant for the final result or are not there. So, I mean, but that's a good point. There is a strong assumption that there isn't a boundary term there. Yeah, that this separates.
The Q corresponds to an integral of the local density. If the density is local, then we can say it's either in A or it is in A.
Yeah, yeah, yeah. That's the statement. Yeah, yeah. Thank you.
Somehow also the symmetry that conductivity breaks down in a conductive symmetry block and differentiation, or it is never?
I mean, I don't know if it necessarily has to be that. I mean, well, it is an internal symmetry of the theory. That's the requirement.
It's mostly one-dimensional systems where the previous symmetries are not broken to do that. So, for example, the same word example.
Mm-hmm.
Okay.
Yeah, thanks. Okay, so the first fundamental object that people defined when they try to compute this is this concept of a symmetry resolve partition function. So this is very similar to the partition function I was defining earlier, this trace of rho to the n, but now we have a projector here, a projector over the sector Q. Okay, so we have different sectors here, different blocks, and we can choose to project over one of them. Now, this quantity has a probabilistic interpretation, especially for n equals 1. You can think of this as a probability that, the probability that if you make a measurement of the charge, you get the value q. Okay, that's what that represents. So for n equals 1 is the probability of getting the value q when you measure the charge. So in terms of that partition function, one can define an equivalent of the entanglement measures that I introduced earlier. So you can talk about a symmetry resolved Renyi entropy or Renyi entropies, and you can talk about symmetry resolved von Neumann entropy. So they are all based upon this new idea, this new partition function, which now depends on the charge of a certain sector, now depends on Q. Okay? Now, something that, for me, at least at the beginning, when I was studying this, was slightly confusing, is that, I mean, it would look from what I said, that somehow you can split the total entanglement into a sum over sectors. And in a way that is true, but the splitting is a little bit more complex than it looks. So the total entropy is not just the sum of these entropies over the symmetry sectors. It's a little bit more complicated than that. And here actually is an example of what happens for the von Neumann entropy. So the total von Neumann entropy is a sum over sectors, but it's a sum that involves various things. So this S of Q is the total, is the symmetry resolved entropy for n equals 1, okay? But this is multiplied by P of Q, which is this probability of measuring the charge to be Q. And then there is also this factor here, which depends again on that probability. So this is Z1 of Q, is this P of Q, okay? So the way the total entropy depends on the symmetry resolved entropies is, I mean, it's non-trivial, it's not just their sum. Okay? There are two terms, and actually these terms, each of them has a certain physical interpretation. So normally people call this the configurational entropy and call this the fluctuation contribution. So, okay, there is an interpretation to all of these contributions. Okay, so these are the definitions, and then, okay, what follows from here is trying to develop some methodology to compute this. And this is what essentially Goldstein and Sela did. They came up with a method that is very general, that we can apply pretty much to any theory, and which is based also on this twist field idea. Okay, so let me tell you a little bit about that. So how do we compute this? So a systematic approach proposed by Goldstein and Sela is based on what I call here composite twist fields. So just to make this a bit shorter, because the others were called branch point twist fields, and then this is kind of a generalization of that. So what is the idea of that? The idea is relatively natural, but there is a caveat, which is this. So what Goldstein and Sela realized is that this new symmetry resolved partition function can also be related to a two-point function of fields. But what is related to the two-point function of fields is not directly the partition function, but it's Fourier transform. So they introduced an intermediate quantity, which they call the charge moments, this straight set n of alpha. And they said, well, if you know the charge moments, in particular for U1 symmetry, but this can be generalized to others, if you know the charge moments, you just have to do this Fourier transform, and you get your partition function. And then from there, you can get your entropies. And these charge moments, these can be related to two-point functions or correlation functions in general of some fields, okay, composite twist fields. So the symmetry resolved entanglement entropy then will follow from doing this Fourier transform, okay? Now, from that point of view, computing the symmetry resolved entropies is a little bit harder because it's not just computing the two-point function, it's then Fourier transforming. And it turns out, even for U1, where this looks relatively simple, of course, this object depends on alpha in a rather complicated way. So this Fourier transform is not that easy to compute. And most of the work that has been done involves many approximations, really. Okay, so the key objects that one tries to compute in the end are these charge moments, and then from there, the symmetry resolve entropies. Okay, so in order to compute that, let me just remind you of some basic ideas about these twist fields. So I introduced them earlier, but I didn't tell you much about them. I just told you that they were related to the cyclic permutation symmetry on replica theories. Now, the way this is encoded in the definition of the fields, which is actually, these are the most fundamental equations for these twist fields, is this idea that you can also represent graphically, that if you have a replica model and you have a field in that model, which now actually there are n copies of it, so you can add a label I, okay? So imagine this is the Ising model again. So in the Ising model, there is a spin field, let's say, and if you have n copies of Ising, there will be n copies of this spin field with a label I. Now, if you take that field on a trip around the twist field, essentially, if you have to cross the branch cut, what this field does is to move to the copy above, okay? And this is one way to represent the symmetry that this twist field is associated with, the cyclic permutation symmetry. If you do that around the conjugate field, the T tilde, what you do is you move to the copy below, okay? So this is the idea. Now, these equations are very important because you can actually construct a form factor program for these fields just upon this statement here, okay? So from this, you can actually deduce the equations for the matrix elements of these fields, and from there, you can compute correlation functions and do lots of things. So this is for the standard fields, okay? This is an old result. I'm just showing it because I want to show you how this generalizes to these composite fields that Goldstein and Sela introduced for U1 symmetry in particular. So first of all, when do we find U1 symmetry? Well, there are quite a few theories where we have that, and there's a lot of work by Pasquale and collaborators in particular, looking, for example, at complex free theories, which have U1 symmetry, so you have two fermions, two bosons, or Sine-Gordon, as I already mentioned, where we did also some work. So it's a symmetry that you have in quite a few cases. Now, if you have U1 symmetry, it's not that different for others, but let's take that. These charge moments I talked about earlier, you can also, Goldstein and Sela showed, you can also write them as two-point functions of some fields. These fields look like the standard twist field. They depend on n still, but they now depend on this additional index alpha, which has to do with the U1 symmetry. And what do these fields do? Well, it's actually quite natural to understand. So there are still twist fields in the standard sense, so they still have the effect that when some field goes around, it moves to the copy above. But in addition, they also have the U1 field acting at the same point, in a sense. So it's a kind of composition between the standard twist field and the U1 field related to the internal symmetry of the theory. And so when a field goes around now, not only moves to the copy above, but there is a phase that is picked up, okay? So it's the composition of the two things. There is a picture of this, which is also a geometric picture, so you can sort of visualize this roughly by thinking of a Riemann surface, which has the standard structure I showed you earlier, but where you now have an additional U1 field sitting on each of these branch points. Okay, so when a field goes around, not only is changing copy, but it's also going around this U1 field and getting a phase. Okay, so these are the kinds of composite twist fields we talk about. Now, if you want to have a slightly more formal definition, perhaps, of this, there is actually a way to define those fields more precisely in conformal field theory, and this is something we did in some previous work. So in conformal field theory, you can actually think of these composite fields as the leading terms of some OPE. Okay, and what OPE, well, again, is the OPE of the standard field, twist field, and a U1 field. So this vertex operator would be a U1 field, charge alpha acting on copy J. Okay, so now we have n copies, we still have the sum over copies, but this is essentially a standard U1 field with a proper scaling in here, which takes into account the dimensions of that field. Okay, so this is how you will define it in CFT, and then you can, as usual, imagine that this definition extends when you put a mass scale in the theory. So this definition, actually, we worked it out quite a long time ago, before anybody was thinking about symmetry resolve entanglement. for different reasons, because actually these composite fields, they don't just play a role in the symmetry resolve entanglement, but they also play a role if you try to think of measures of entanglement in non-unitary conformal field theory or quantum field theory. So in non-unitary theories, this composition comes about because the twist field of lowest dimension is no longer the standard one, but it's the composition with the field of lowest dimension, which in a non-unitary theory can have negative dimension. So you get also composed fields like this. Now these fields have their own conformal dimensions that you can compute. It's the sum of the dimension of T plus the dimension of the U1 field divided by N. So that can be computed using conformal maps. So all these things are known. And once we have all this information, you can, for example, develop a form factor program to compute matrix elements of these fields. So this is something that David and Pasquale did very recently. And from there, there's lots of different models that you can study. And I have to say, although I haven't cited all the papers here, that Pasquale and his group have done a huge amount of work on this, and very, very nice work. So I should certainly acknowledge that. Okay, what are the main ideas or results in there? Also, how will you then, use these ideas I just presented? So let me give you a sketch of the sort of calculation that is done in many of these works, and actually in our own work, some of the things I mentioned. So the thing, the computation usually goes as follows. So you want to compute this two-point function. Let's start with the ground state for now. It's hard enough. And well, if you have a certain experience computing things based on form factors, what you would want is to do an expansion of this into matrix elements of these fields. So this is what these Fs here are, the form factors. In one dimensions, this will depend on rapidities of particles on the state. It will depend on particle species if there are several. And so you have a sum of an infinite number of terms, which is, however, very strongly convergent for big distances, for big L at least. So you have this kind of expansion. Okay, that is complicated enough. And you have to remember that to get the entanglement, you still would have to Fourier transform this in alpha at the end. So it's even more complicated. Now, it is actually so complicated that, in fact, what is very often done is to actually only consider the trivial term in this expansion almost, the disconnected part of the correlation function. So this might seem a little bit underwhelming just to take the term with p equals 0, which is the Beth squared, but actually, even if you just consider that term, this Beth square, you can already get some of the properties of the symmetry resolve entanglement that Sierra and others were talking about in this abstract I read at the beginning. So a lot of information already comes simply from considering the first term, okay? And there are works where people, of course, consider also other corrections, okay? Now, in 1+1D QFT, these Beths, they have a very specific structure. So they are complicated functions of all parameters, alpha and n. But what is known is that they have to scale with a mass scale to the power of twice the conformal dimension of the field. So at least the scaling with mass, this is known precisely how it has to go. And this constant, well, it depends on how you normalize the fields, okay? It turns out that for many models that people study, when you do the Fourier transform of this function squared, you can actually argue that the main contribution to that transform comes from alpha around 0, and then you can use a saddle point approximation to get the leading contributions, okay? Now that is very technical, but I just want to show you very quickly a couple of formulas from our papers, okay, kind of final results. So for example, if you do this kind of analysis for sine Gordon, which we did in one of our papers, and you do the kind of approximation I mentioned, what you get for this symmetry resolved Renyi entropies is a formula that looks like this. So you have the logarithmic scaling that Xavier Alcaraz and Sierra were telling us about. So it is there. So this, you can think of M as the inverse correlation length, if you prefer. So you have a scaling with correlation length with the usual coefficient for Renyi entropy, so proportional to C equals 1 for sine Gordon. Then you have some constant, so this D is a constant, doesn't matter where it is. And then you have this negative log-log term, just as they were telling us in their abstract as well. And not only that, you see that this term actually depends on some constant here, delta. That delta is actually the conformal dimension of the U1 field in Saint-Gordon in particular. So you see that just from considering this BEF contribution, you get actually three of the properties that were mentioned: the log scaling, the log-log correction, and you also get this equipartition. So you see that none of these terms depends actually on Q at all. And that's what they call equipartition of entanglement. Now that is not in general the case. So if you consider other corrections in M and L and so on, you will see that it depends on Q. Okay, so this is a kind of first order observation. Now you can do a similar calculation, for example, for Potts, for other theories. We did, for Potts model, we also did this. The difference is subtle, but Potts model is a discrete symmetry. So the Fourier transform is actually a discrete Fourier transform. It's a sum, and that sum can be performed in this case. So it is possible. I mean, this is some complicated correlators. That doesn't matter, but you can see that, yeah, there are some contributions, which is the standard entanglement, so essentially the log term, a constant, and then you get things that depend on Q. So you have the dependence on this charge that appears there at a higher order. Okay, so this is actually two formulas from two of the papers I mentioned, and that's all I want to show from there, because getting here is just a very technical calculation, but not particularly interesting for a general audience. But having done these works, one thing that occurred to me is that, yeah, it was terribly difficult to sort of go beyond this first order. You just get some very horrible expressions, and it's hard to find a meaningful interpretation for them beyond doing a very complicated calculation. So one thing that I thought about was that it would be nice to find a model or a kind of states, perhaps, where one could do things more explicitly and get formula that are a little bit more close. And that's how I came to think of doing these excited states I'm going to talk about. Yes? So it would be for large L, so large separations, yes. And it's also, I believe, there is also an expansion on this log M epsilon, so this is also taken to be small. So epsilon is a UV cutoff, M is the mass scale. Okay, so there's a, so essentially it's, yeah, log M epsilon small, modulus small. Okay, so it's a double expansion in a way. You need both. I mean, so the expansion on large L comes from the form factor expansion, and the expansion in small log M epsilon comes from the saddle point approximation around alpha 0. So there's lots of approximations that go into this, unfortunately, if you want to get an actual result. Yeah. Yeah? Yes. Yes. Yeah. Yes. Yeah.
So how do you know in advance which symmetry to look at?
I mean, okay, so I don't know so much about that connection, but the way I come to this is from S-metrics perspective, let's say. So Ricardo says she cannot hear the questions. I guess it's the microphone thing, yeah. So I don't know about that connection, but what I can tell you is that one way you can come to Potts model, which is where I come at it from, is from the S-metrics point of view. So you have a quantum field theory formulation of Potts, which has a very particular scattering matrix with a particular symmetry. And in that context, I think there is no doubt what the symmetry is. Now, how you connect to ON, I don't know precisely. Yeah?
In the analytic continuation, you lose the actual ON symmetry, and here you actually need it quite explicitly, as far as I understand. So, I mean, maybe you can do that, but after analytic continuation, also in that N, which is an additional complication. So, you might be, and I don't know. It's not clear to me, like from what Olalla explained, that
Thank you, Ricardo. Sorry, there was a problem, but we are back. Okay. Yeah, so, okay, let's continue. So I was just telling you that, okay, there's things that we can do for quantum field theory, but in essence, it's quite complicated to even get to the simplest results. So at this stage, I started thinking that perhaps we could think about other systems or other kinds of states where we can go a little bit further with this sort of calculation and get some more general results. And the kind of states that I thought about were a particular family of excited states. I thought about that because in the past, 4 years ago, we wrote a series of papers about the entanglement of these states. So I knew that these are states that have very special properties when it comes to entanglement. So I'm going to tell you a little bit about that in the last part of my talk. It's a bit different from what I came before. So excited states. So we want to look at excited states in massive quantum field theory. And these are states where there is a finite number of excitations above a generally non-trivial ground state. Okay, so in 1+1D quantum field theory, if you want to get an idea of what this would look like, this would be states that are still in replica models, so everything is always n copies. But in general, a state of k particles in an integrable QFT or 1+1 dimensional QFT, normally you can characterize it by a set of rapidities and quantum numbers. So essentially you have a state characterized by a set of rapidities and, well, you have to replicate it n times. So that's the sort of state we are looking at instead of the ground state. And what's important here is that this k is finite. So we have a finite number of excitations. Now, what we're going to do is to look at the charge moments for this kind of state and then at the symmetry resolved entanglement entropies. Now, if you try to do a calculation for this state in complete generality, this is still very complicated. I mean, I just told you that doing the ground state was complicated, so that would be even more so. But what is interesting is that there is a specific scaling limit where things become a lot simpler, okay? And the scaling limit I'm talking about is the following. So we have a system of a certain length, L, capital L. We have a subsystem of length, little l. And what we're going to do now is to consider these two scales to be very large, but in such a way that the ratio is fixed. It's fixed to a value between 0 and 1, obviously, because L is a subset of big L, okay? So in what I was telling you earlier about ground state, what we were doing was quite different. We were starting from the beginning of the calculation in infinite volume, and then we were considering a finite region already in that limit. Here, instead, both the volume and the region are infinite, but at the same time with a fixed ratio. Now, this sort of excited state with this scaling limit is what we call a zero density excited state, because we have a finite number of excitations in an infinitely large system. Now, you can imagine that in this limit, many simplifications occur. It's pretty much as if those excitations, as if they never saw each other, really. So in this limit, actually, interactions matter very little. There are very few things that matter when you try to compute a result, for example, for the entanglement. So I'm going to remind you of some of the results we got for the total entanglement. So this is not symmetry resolved. This is the work we did in 2018-19. We wrote 4 papers about this with Benjamin, that's here, with my student, Cecilia, and my former postdoc, István Széchenyi. I have to say that actually our work has been extended a lot by Zhang and Rajapur in recent years, and they're still working on this topic. And they looked at many extensions and also specifically at spin chain problems. So what is the result here? So the result that we got in those works is easy to explain. It just said that once the ground state contribution is subtracted, so this is a result not for the entanglement entropy, but for difference of entanglement entropies. The entropy of the ground of the excited state minus the entropy of the ground state. So once you subtract the contribution of the ground state, the entropy that remains is a very simple function of R, just essentially a function of a polynomial of this R, which was the ratio of sizes. Depends on that, depends on the number of excitations, and it's going to depend on the statistics. So essentially whether they are identical or not. But that's all that enters in these formulas. So I just show you an example, the simplest case. So there's a delta here indicating increment of entanglement. So this is Renyi entropy for one excitation in the excited state minus the ground state. The difference is just this simple formula. The entropy in the ground state is complicated, okay? So the entropy in the excited state is complicated too, but their difference is very simple, okay? So the excited state adds this contribution to entanglement. And it depends on R in this very, very simple fashion. If you take limit n to 1, you get this similar formula, this related formula for the von Neumann increment, okay? Now, one excitation is very simple. Obviously, you want to extend this, and we did in our work. For states with more excitations, distinct, not distinct, you can find similar formulas, and they are always polynomials on these two scales, okay? There is a simple reason for that. I'll come to in a minute. But before that, let me just show you a few pictures for other examples. So this is from one of our papers. So all of these pictures are increments of Renyi entropies for different kinds of states. And what you see in each of them is, well, a bunch of curves. The one at the top, this is the von Neumann entropy, so N1. The one at the bottom is the opposite limit, n going to infinity. That is also a measure of entanglement. It's called the single copy entanglement. And then in between, you have different n's, okay, increasing. So all these curves have similar structure. Of course, they are symmetric around r equals a half, where they have their maximum. What these indices represent, for example, in the first one, what you have is a state of 10 identical excitations. That's what it means. And then in the others, for example, this one is a state where you have 5 excitations, 2 of which are identical and 3 of which are identical, but different from each other. Okay, so you can do little groupings of identical, non-identical excitations and build these formulas systematically. So there's kind of some building blocks that you can put together to get any possible case. Okay, so this is for the total entanglement. Now, what happens if you have also an internal symmetry in this situation? What happens to this symmetry resolved for entanglement entropies? You can imagine that they're going to be simple as well. So that's what we will find. Now, I just wanted to tell you a little bit about the range of systems where these kind of formulas hold. Okay, so these formulas, as you have seen, they're very simple. And because they are so simple, actually, they can be obtained in many different ways. Okay, so they hold for many different systems. So one way in which one can obtain them is simply by semi-classical arguments, semi-classical or probabilistic arguments, where these R and 1 minus R become the probability of finding an excitation in region A or region A bar. And essentially, if you think of it that way, you can derive all of these formula. Now, we were particularly clever because we managed to derive these very simple formulas in the most complicated possible way, which is by using form factors. But we did. And it's interesting that one can actually do a full-fledged quantum field theory calculation, and in this scaling limit, we get these same polynomials. Okay, so this we did actually for free theories. Okay, it was even too complicated for interacting ones. One can actually get the same formula if you look at magnonic states. So if you look at a state of a single magnon and you compute its entanglement, turns out that in this scaling limit, you get the exact formulas here. But that's for the total entanglement now. There is no ground state, it's just that state. And what's interesting is that for these states, there can be interaction, but you still get these formulas. Okay, so the interaction doesn't seem to change the result. You can also get these formulas from simple qubit states. So for example, the formula for one excitation I just showed you, you can also get it if you compute the Renyi entropy of this state here. So it's a cleverly constructed state where this root R and root 1 minus R are kind of giving you the probabilities that there is one particle in region A and 0 in region A bar, and this is the opposite situation. Okay, and you can construct other qubit states that will give you other formulas of this family. Turns out that in free theories, you can even show these formulas hold in any dimension. So if you replace this R by a ratio of generalized volumes, you still get this kind of formula. And you can also get them, for example, in highly excited states of CFT, which is something that's been done recently by Ricarda, Pasquale, and Luca. So a wide range of very different systems. Why does it hold in so many cases? Well, it turns out that the only thing that is actually important for these formulas to hold is that the excitations are localized. So when they are not localized, they failed. But if they are localized, then you will find this. And localized, however, can be defined in different ways. So it could be that you have a gap, and so the correlation length is much smaller than the region of the subsistence size. That's what typically happens in massive QFT. But you could also have another scale, which is this, the inverse momentum, so the Broyle wavelength of the excitations. And if that's much smaller than region size, you will also get this formula. And this is something you can actually satisfy if you are in CFT, but for excited states of high energy. That's why one also gets the formula in CFT by a completely different method. Okay, so there's even another, well, I mean, the semi-classical viewpoint has actually been generalized even further recently by Giuseppe and Jacopo. So there is an extension of this even to systems where there is an interaction potential. So it's all, okay, they're very, very general and applicable in many cases. So what about these charge moments, okay, or symmetry resolved entanglement? So we're now going to think about these same formulas, but for a theory, for example, a complex free boson thing. So if you take a complex free boson theory that has a U1 symmetry because it's complex, and so you are in a situation where you have a free theory and you have an internal symmetry. So you should be able to repeat this calculation, but now for the symmetry resolved entanglement entropies. And indeed, you can do that. The techniques, the form factor technique is the same. All the cases I mentioned, magnons, qubits, and so on, they can be still done. But what the calculation gives you is not the entropy directly, is actually now the ratio of charge moments. Okay, so it gives you the ratio between the excited state and the ground state. This is what you get naturally from a form factor calculation, for instance. So let me just give you some examples. So if you have U1 symmetry again, and you consider a state of one excitation of charge epsilon, you find by a form factor calculation that the ratio of these charge moments, in this case, looks like this. And if you remember the formula I showed a couple of slides ago, if you put alpha equals 0, we already saw this kind of polynomial, r to the n plus 1 minus r to the n. So now when you have this U1 symmetry, what it does is to essentially differentiate region A and region A bar. So if the excitation is in region A, it's going to contribute also a U1 phase that you see appear in the formula. And you can do this for the state. So for example, if you have a state of two particles of opposite charges, this is the sort of formula you get. If you have a state of three identical particles of the same charge, you get something like this. And you can almost work out in your head already the combinatorial nature of all these things. So these are just binomial coefficients, and it's very, very simple. You can, well, do other examples. So these pictures I showed you at the beginning, these are actually numerical evaluations of this formula. So the dots are numerical and the lines are analytical. And what's plotted here is actually the real and imaginary part of this function for this state, which is a state of two particles of the same charge, but different momenta. So the formula doesn't explicitly depend on the momenta, but the fact that the particles are distinct has an effect on what this formula looks like. So it gives us a square in there. So, so you see that the agreement is very good. This is a numerics that was done for a complex harmonic chain. So this is a model which is discrete, but in the scaling limit should give a complex free boson. Okay? So, so it works nicely. So just to remind you what these M's are, so M psi is the ratio of these charge moments for the excited state and the ground state. Now, suppose that you want to compute the entanglement entropies. I just have 2 slides left, so it's not too much. If you now want to compute entanglement entropies from this, you need to Fourier transform. But what you need to Fourier transform is actually not this whole formula, but just the top, because you want the entanglement of the excited state. And so you have to, well, you have to see if you can do that. Okay, so the important quantity is this ratio multiplied by the ground state contribution. Now here is where the simple structure of these ratios is useful. Yeah, okay. let me just, I think I said these things. So what we need to compute is this product, and then it's Fourier transform. Now, well, this doesn't seem too complicated, but the only thing we have to make sure is that this ground state contribution actually makes sense on its own in this limit. So all the time we have been taking the scaling limit in this ratio. So we have to make sure that both numerator and denominator have a finite limit on their own. And that is actually the case. At least in QFT, it's easy to argue this, because as I told you earlier, the ground state charge moments, essentially these are the backing expectation values of this composite field. And this backing expectation value is well defined, and it's not divergent in this limit of infinite volume. So this product is a well-defined quantity. That's all that I wanted to say. And so one can try and Fourier transform it. Now, if you try to do that Fourier transform, you can see that this is very simple, because so we want to compute this partition function. For example, for one excitation, we have the ground state moments, charge moments in there, and then we have our formula that I just wrote. Now, even if you don't know what the ground state contribution is, well, we know, the Fourier transform is kind of trivial. It's just the Fourier transform of this function, or the shifted Fourier transform of this function by this phase. So essentially, we can write everything in terms of data that relate to the ground state. Okay, so one can write closed formulae. They are not completely explicit. They will still depend on the ground state. But at least we can say that if we know the information about the ground state, then we know everything about these excited states. Okay, so in that sense, we get closed formulae, which we couldn't get in general before. Symmetry resolved entanglement would just be the ratio of formulas like this. So for example, for one excitation, this is the sort of thing that you would get in terms of ground state partition function. So this can be related back to the ground state. For other states, this is more complicated, but in essence, the same idea holds, because all of these formulas just involve phases, and these are very trivial to Fourier transform. And if you look at other types of states for which one gets these formulas, it's even simpler, because, for example, if you look at states of 1, 2 magnons, in that case, the ground state essentially is trivial. There is just the magnon state. So that is the limit where these partition functions, essentially, they are all 1. And so you get a very nice, simple polynomial. Everything is a function of polynomials in R, and has an interesting probabilistic interpretation as well. So let me just conclude, just to say that I reviewed the definition and some properties of this symmetry resolved entanglement entropies. I tried to give you an idea of how this can be computed in quantum field theory, and how using quantum fields is useful in this context. In general, it's technically quite difficult to get analytical results, but the excited states that we've looked at, well, are probably the nicest situation. At least we can get lots of things analytically and in closed form. And well, an immediate follow-up from here, but that's is just to look at, of course, other entanglement measures. So this is something that one can always do. So in the same way, there is a symmetry resolved for Neumann entropy and Renyi entropy. There are other measures that have similar generalizations, like negativities. And if you are somebody that likes form factor technology, then of course, there's still the problem of looking at all these higher order corrections and understand better, for example, how the equipartition is violated, and in those corrections and so on. So thank you very much for your attention, and that's all I wanted to say.
Thank you. Since there are people online, let us use the microphone.
Hi, thanks for a nice talk. As you might guess, I want to ask about spin chains. So, in the for an infinite spin chain, where you split it in two, then, as you know, the reduced tensor the reduced transfer matrix is the exponential of some integer valued operator, which is the corner transfer matrix Hamiltonian. So you can get the normal Renyi entropies as characters, but these resolved Renyi entropies, if you form a generating function for them, then that's just a generalized character in this picture as well.
Yeah. Okay.
So have people done that, and is that useful? Or?
So I don't know. Is the honest answer. I don't know if people have thought of it that way, but as I said at the beginning, actually one of the earliest works, or probably the earliest work where people looked at this in the context of spin chains is the work of Xavier Alcaraz and Sierra. They look at XXZ. I don't think they thought of it in this way, but probably it could be translated in this language, and it would be useful because it's probably more general than what they did. But I don't know if people have seen it in that way.
But generally, is it a useful approach to get the generating function for the resolved things by summing over all q times z to the q? Or,
I mean, I think it would be, yes.
Yeah. Okay, thanks.
Thanks.
Other questions?
I have a comment on the limit, this limit you did where you define everything in terms of this little r.
Yes.
So my understanding of the work of Musardo and Vitti is that this limit is kind of fake in the sense that it's not many body physics, it's just a single body or few body features in which the entanglement entropy is dominated by the classical, probabilistic argument. I mean, for example, go on, which is related to, you can get from simple probabilistic, this S1 is R log R minus, this is simply probabilistic, whether the particle is in that region or not.
Yeah, I mean, I agree.
So it's not really a many body, it's a limit, it's not really a many body property at this point.
Well, I mean,
rather a classical.
It's certainly, I mean, what you say is certainly true, and it has actually been known for a long time that there is this semi-classical picture in which you can get this. So that is true. At the same time, somehow there is some many-body information that is hidden there, in the sense that if you compute this in quantum field theory, in massive QFT, what this gives you is a difference of entropy. So this is only simple because you are subtracting the ground state entropy. So if you were to compute the total entropy of that excited state, there would be a component that is fully quantum, and it's very complicated. And so what you're saying is that whatever you are adding on top of that for this excited state, in this particular limit, is actually very simple. And it's very simple, essentially for the reason you say, because in this limit, you have an infinitely large system with very few particles in it. So it's as if they never saw each other. And the contribution that they give is purely probabilistic and purely classical. But the kind of non-trivial bit is hidden in the increment in there. Yeah, so there is something quantum still.
Yeah. Other questions?
Yeah, again, this somewhat heretic questions from somebody who's not working in this field. So what are you learning about the quantum field theory by calculating this symmetry resolved entanglement? I would say that things I would be interested in is things you measure, like correlation functions of local operators. But what is the use of this?
What is the use? Well, depends what you're interested in, I guess. But I mean, one way you could think of it, I mean, maybe that's not so QFT, but well, it kind of gives you information about the structure of the reduced density metrics. So in particular, if you look at the discrete system, that would be even more useful, I guess, because I mean, so you could think of this as having some numerical application. So if your reduced density matrix has a block structure, and you can somehow assign a contribution to entanglement to each block, then perhaps you can study the blocks rather than studying the whole reduced density matrix, which is a much bigger object, if you wish. So it kind of at least has a use of reducing the problem to something that's slightly simpler. It tells you something about the structure of the reduced density metric. So it tells you it's not just random metrics with randomly distributed entries, but actually there's a structure that's due to the symmetry. So it gives you that kind of information. A lot of people are interested in this because apparently it can be measured experimentally in a more accessible way than standard entropies. From a QFT viewpoint, I mean,
like 2 point functions and then reconstruct these things.
I don't know. I don't know the details to tell you that, but I think the measurement is pretty direct. I mean, at least if you look at the papers, we have curves for the, for the entropies, yeah, and for the contributions by charge sectors. So I think it's, yeah. Well, I think that might be other work as well. Yeah, yeah, maybe. I mean, maybe that's even other work, but there are some more recent papers where they look specifically at symmetry resolve and kind of charge sectors and all that. So, I mean, I don't know the details, so yeah, it's not fair to comment.
The charming thing about this is that it somehow naturally falls out to the numerical evaluation. It's something that is calculated anyway. It shows that the way the algorithm works. For the global,
yeah.
For the symmetry resolved one? Sorry.
I mean, I think, yeah, technically it's probably not that different. And indeed, it can be evaluated with DMRG. And I think people have done it for many examples. I mean, I think they're not very substantially different, but then you have this extra, step, which is Fourier transforming to get the entropies. So in that sense, it's a little bit more complicated. But I mean, I speculate that perhaps the advantage is that you can work with the smaller systems because you can look at the blocks rather than the whole density metrics. Yeah. So, sorry.
Yeah, okay, thank you very much.
It's a partial answer.
Other questions? If not, thank you again.